All right. Hi guys, this is objective 1.7 where we are constructing, identifying, and describing rotations of geometric figures. So the goal here when we're thinking about rotations is like, oh, you see this little buddy, right? If we spin this little buddy around, that's like rotating, right? So that is, hey, having the best time, rotating, wee, right? Okay, that's like what a rotation is. So let's start with some important vocab for today's lesson. So first is transformation. A transformation is just when we alter a shape. We just alter the way the shape looks. We don't turn it into a completely different shape. We just alter the way it looks. A rigid transformation is a transformation where size and shape stay the same. Okay. Now, when we do rotations, we're going to use quadrants on that coordinate plane. So when we look at a coordinate plane, where we take that flat x-axis and that vertical y-axis, and it splits it into 1, 2, 3, 4 different what we call quadrants. The first one we label with 1. This is quadrant 2. This is quadrant 3. This is quadrant 4. When we do rotations, we also deal with angle measures. Because when we rotate something, it's like a circular motion, which is, we can describe circular motion with angle measures. So as a reminder, an angle measure is, one angle is when you have, two rays that meet at a common endpoint. And then that circular path in between the two sides of your angle, that's the measure. So this looks like it's like, I don't know, maybe I'm going to call it a 30 degrees. And then we're going to use regular polygons in today's lesson. A regular polygon is just a shape with all congruent sides. Okay, and then lastly, we're going to talk about, when we talk about rotations, there's two ways you can rotate an object. You can rotate an object clockwise. So that's in the order of a clock, right? So when you're sitting in class, right, and you're watching the minutes go by and wanting the day to end, right? So you're watching, as you're watching the clock spin, it's going clockwise. Counterclockwise is the other way. I like to also think of it, it's like to the right or to the left. Okay, so that's the vocab. In class, we talked about rotations. We were talking about like a video game, designing a race car for a video game. And we were talking about when you do have a race car and like the wheel spins, that's a rotation, right? We're going to skip over this part for now. It's okay if you don't get that in if you were gone. And we're going to jump to the key points box on page 2. We're just going to learn some stuff that is true about rotations in general. So first, a rotation is a rigid transformation, so the size and shape stay the same, involving circular movement around a center of rotation. Do you have a fidget thing? Or is it? Oh, it's like literally right in front of me. So this is like an example of a rotation. So when we take this, right, we're rotating this little fidget guy, right, around this center. The center doesn't move, notice, right? We're just spinning all the points on the outside around that center. Okay? So I'm going to go through kind of this example to kind of see some more. So how we can see this in like shapes and geometry is, let's think if E is rotated counterclockwise, so to the left, about 0.0, to C in the regular polygon below, we're going to respond to the following. So we're going to think of a few things first. So my goal is, I'm rotating E about 0.0, so that at the center of rotation is O, to C in this regular polygon. So like I can think of my center as O, right? I'll put this black dot at E. And my goal is to rotate it counterclockwise to C right there. Okay? So that's the rotation. Starting at E, counterclockwise to C. Okay? So let's first compare the length of OE. So the center O to E. When I place E prime anywhere else under after a rotation, the length of OE to O prime E prime is not going to change. Okay, well actually, I don't want to write stay the same. I want to write same length. These two segments would have the same length. Okay? When we rotate something, right, when I rotate this like black dot as E and I rotate it to a different spot, the distance the black dot is from that center of rotation isn't changing. Okay? So let's fill in here. The image and pre-image will always be the same distance from the center of rotation. Now, when we're rotating, again, we're rotating, it's a circular motion, so it's an angle, right? So when I rotate O to E, right, that's kind of like a circular motion, or if you can see it with like a paper clip, O to E, that's like a circular path, right? So that's creating an angle. So we call that an angle of rotation. And what's cool is if we're inside a regular polygon, so this is a regular polygon, we were told that, all these sides are the same. And so that means it's going to be split into 1, 2, 3, 4, 5 congruent angles. So I can think of like splitting this into like 5 congruent parts where each one of these angles, the distance from here to here, the rotation from here to here, the rotation from here to here, the rotation from here to here, and the rotation from here to here is all going to be the same measure. When we think about how many degrees that is, what we can do is know if the entire rotation around a circle is 360 degrees, and we're splitting it into 1, 2, 3, 4, 5 parts. 360 divided by 5 is 72. So the angle of rotation for each, as I go from each point, or as I rotate each one of these sections, each one of these angles is 72 degrees. The rotation from A to E is 72. From A to B is 72. B to C is 72. C to D is 72 degrees. D to E 72 degrees. So now I'm going to actually perform a rotation. So it says perform the following, and then, whoa, there's some language there. This is function notation, what we're seeing right here. Function notation is, we saw this in the other transformations, where instead of saying, hey, let's rotate point E this many degrees in this direction around this center of rotation, that's like a lot of words. Instead, we can use like letters and symbols to describe the rotation. So this is how we are going to use letters and symbols for a rotation. So first we use a capital R. You might remember for reflection, we used a lowercase r. That stood for reflection. A capital R stands for rotation. Then, I want you to notice there are 2 pieces of information here. There is an O, so there's a letter there. That is the center of rotation. It's like, what are we spinning around? What place, what spot are we spinning around? And then the second piece of info, you see it's like a number with degrees. That is the angle of rotation. So that first letter, again, center, and then the degrees there are the angle of rotation. And then you put in parentheses, what shape am I even spinning? To equal what new image? So other important stuff to know is that rotations are typically, at least in math, counterclockwise. Unless otherwise stated. So if I just tell you, hey, rotate this, if we're in math class and I'm like, yo, rotate point E, 72 degrees, about 0.0, you can assume that that's counterclockwise, the direction. We also use positive degrees to represent counterclockwise rotations. And we use negative degrees to represent clockwise rotations. So when you're looking at the notation, and if you see positive degrees, that means the direction of the rotation is going to be counterclockwise. If you saw a negative 89 there, then the rotation would happen in the clockwise direction. Now, that might seem weird to you because normally when we think about clockwise, like clocks and rotations, we think clockwise. It's because back to the coordinate plane, the quadrants are ordered in a counterclockwise order. It went 1, 2, remember it went 1, 2, 3, 4. So that's why in math, the rotations are counterclockwise typically. Okay, so all of that is now going to help us interpret this language to perform this transformation. Where it's like, what are we doing here? We're rotating about, that's a typo, team. I'm sorry. Put an O there instead of an E. Okay. We're rotating around O, 216 degrees. And what point are we rotating? We're rotating E. So, and the question is, at what point would E prime land when we did that? Well, let's think about it. If I rotate E, again, counterclockwise at O. I rotate it to point A, that's 72 degrees, right? If I rotate it, which is not 216, right? If I rotate it to B, it's 72 more degrees. 72 plus 72 is, 144? So not 216 degrees. If I do another 72 degree rotation though, is 72 plus 72 plus 72 216? Yes, it is. So where does that land me? At point C. So C is the answer here. Because it took 3 72 rotations, so from E to B all the way to C to get to move E 216 degrees. Okay, so that's how we could use regular polygons to kind of help us figure out rotations, and the light practice will kind of show us that. We're going to jump now to, and you could also use, if you're not going to use a regular polygon, you can also use patty paper, right? So patty paper is really useful if I'm just going to show you this really quickly. If we're going to transfer a point in degrees of 90, so if I want to take this point and rotate it 90 degrees, if I turn and I want to do it about the origin, right? If I turn my paper, sorry, there's no way for me to pause this stupid thing. If I turn my paper one time, that's where it would end up. That would be a 90 degree rotation. And notice, I don't want my center of rotation to move. So I'm going to trace my center of rotation 2, so that when I stab here, I keep my center of rotation in the same space, okay? So that's 90. If I do it one more time, that's 180. If I do it one more time, that's 270. And then all the way back would be 360. So that's how I can use patty paper too to perform rotation. Okay? All right. Now we're going to jump to page 5, where in class we did some rotations with patty paper, and we discovered there's some patterns on the coordinate plane when we rotated 90, 180, and 270 degrees. So those patterns we can describe with mapping notation. So mapping notation is when we like talk about what's going to happen if we put our rotation on the coordinate plane, and it's like what is always going to happen to the x and y coordinates after a certain rotation. So if we're on the coordinate plane and we rotate something 90 degrees counterclockwise, what will happen always is that xy will map to opposite y, x. Meaning what will happen to the coordinates always, the new location of the image will be x and y will flip spots and y will become the opposite sign. So, for example here, if we have triangle XYZ with these three coordinates and we want to rotate 90 degrees counterclockwise and we're going to give the coordinates of its transformed image, what I can do is take the original coordinates, and then to find the prime coordinates, all I have to do is flip around y and x. So I'm going to switch these two spots, and then my y is going to become the opposite value. So it was a -1, so now it's a +1. X stays the same sign. For y, if I have 4, -3, y prime is going to be, again, they're going to switch. We're going to switch. And then the y value is going to have the opposite sign because of the negative in front. So it's going to be +3, 4. Notice it's not saying that y is always going to be negative. It's saying this negative sign means flip the sign. Okay, and then z would be -2, 1. So z prime, 1 would go up front, but it would become negative because it was positive, so it's flipping the sign. And then x stays -2, but now goes second. So that's what will always happen if we rotate an object 90 degrees on the counterclockwise on the coordinate plane. Let's talk about what happens when we rotate 180 degrees counterclockwise. When that happens, xy will map to opposite x, opposite y. Okay? So this was the 90 degree rule. This is the 180 degree rule. So if we take our triangle again, we have those 3 points, and now we're rotating 180 degrees counterclockwise. Here's how I can find my prime coordinates. If x is at 2, -1, x prime is going to be at, just change the signs, -2, now +1. If y is at 4, -3, y prime, just change those signs, -4, and then +3. If z is at -2, 1, z prime is going to be at +2, -1. I just flipped those signs. Okay, last one is when we rotate 270 degrees. When we rotate 270 degrees, what happens is xy is going to map to y, -x. So again, x and y flip spots, but now that x coordinate becomes the opposite sign. So again, if I'm rotating a triangle 270 degrees counterclockwise, and I want to find the coordinates of the transformed image, what I can do is, if x is at 2, -1, x prime is going to be at, that y value goes first. I keep the same sign. I'm not flipping the sign, so it still says negative, but then the x one I have to flip the sign, so it's going to become -2. Y, if it's at 4, -3, y prime is going to be at, now again, y goes first, and it doesn't flip the sign, right? This doesn't just mean positive y, this means keep it the same. And then 4, that goes second, and now I need to flip the sign, turn the positive into a negative. And then z is at -2, 1. Z prime is going to be at, y is +1, so it's going to stay the same sign. X is -2. It's going to flip sign, so become positive and now go second. So that's how I can find the coordinates of the image. Okay? And that is it for this lesson. Hope that made sense. See ya. Bye.